Hello again. So in this talk, I'm going to talk about the GE Predix Time Series ingestion application that we built in collaboration with GE, which is being used in the Predix IoT system that I talked about earlier in the keynote. That's the cloud platform that they use for ingesting IoT data. So just a quick synopsis of what I'm going to go through. I'll just give a very brief overview of the GE Predix platform. I'm not a Predix expert, so it'll be just a very high-level overview. And then the Predix Time Series application, why Apex was chosen, and what are some of the learnings when this application was built on top of Apex. And I'll take some question and answers at the end. Okay, so what is Predix, right? So GE has, is a big company, right? It's a 100-year-old company. It's got its footprint in almost every nation in the world, and they do everything, right? So they have deep-sea oil rigs, machinery in deep-sea oil rigs. They have engines in airplanes, powered locomotive, you name it, right? So all these machines, they have a lot of sensors in them, and that produces a lot of data. So their traditional approach was actually, doing the compute on the edge, right? So put the compute where the machines are, closer to there at the customer sites. So they would actually ship software, and basically that was getting unwieldy, and all the problems, right? Updates and issues and fixes and so on. So they basically wanted to build a cloud platform, so essentially they can move all the analytics to the cloud. They can be more agile, adaptive. So they just want to basically ship all this data that's being produced by these sensors live into the cloud. So now that poses a problem because now you're bringing a lot of data, right? So a typical customer of GE can have millions of events per second, just one customer, right? In one site, actually, one customer in one site. So they need a very fast platform that can handle these data in real time and perform some type of analytics on it before they can land it and do further deep machine learning and so on. And then of course they also have built a marketplace around it. So they apart from the ingestion, and they also provide some other analytics services and views and dashboards and so on. So you can check it out. So this is a slide I actually borrowed from my GE co-presenter who wasn't here today. But so just to show you that this is not your household IoT, right? It's not your lights or your thermostat producing data. It's these windmills and really industrial machinery that's very critical, and they can't go down, right? So typically what they do is when they get this data, they first want to filter this data, parse the data, clean it up. Then they want to apply certain rules to it if they can. And then they want to basically store it and then apply different kinds of machine learning models on it so that they can predict failure. So for example, if one of these windmills is going to fail, they can basically do that. They can know that ahead in advance so that they can take corrective steps. So this is the Predix architecture. So what they do is they have what's called a Predix machine that they put on the customer site or the site where the data is being collected that pumps the data to the cloud, to the GE Predix cloud. And then they have a high-performance gateway there that's receiving this data and then distributing the data for different kinds of processing. On this cloud side, they use Cloud Foundry and other I think different cloud providers so that they can get the scale that they need. And then we are part of that Predix cloud infrastructure. So when it comes to ingesting this data and performing lightweight ETL and rule-based analytics, they use Apex. So here's so what are these sensors sending, right? So these sensors are basically sending some data that they're measuring. So if it's a pressure sensor, it could be a pressure reading, or if it's a temperature sensor, a temperature reading. And they're doing it more than one time, once a second or even quicker than that, right? More than one time a second. So each reading comes in with the value, the timestamp, and a quality, what kind of quality, how confident is that reading. So all this data needs to be ingested without any loss. So you cannot drop any data, because what happens is there are rules and that happen based on successive values, right? So for example, if a temperature reading suddenly changed, that could indicate a malfunction in the future, right? But if you lost the second reading and you basically have the next reading after that, the temperature might come back to normal. So it might look like everything's fine, right? So we have to be able to ingest all this data in a fault-tolerant way where we cannot lose anything, right? And basically, these sensors could be even the data generation could be even at a millisecond level. Sorry. Oh. Okay. So this is the like a zoomed-in model of the Predix Time Series architecture. So you have data coming in from these gateways, and then they use the application the time series application to ingest the data, clean it up, and store it. Apply some rule-based alerting, then store it, and then they apply machine learning on top of it, generate the results, and then they have a view API on top that they can use for their downstream applications, and basically the customer can perform different types of queries and then look at the outputs. So what are some of the queries that they support? So on these metrics that are collected, you can actually basically do different kinds of analytics like aggregates, like average, sum, count. You can do SQL type queries like limit, order by, and then you basically expose these as web services. So basically you can do get and post to retrieve the data. But this is mainly for the downstream consumer. So I'll briefly skip this slide because you already guys know what Apex is. So it's a in-memory data in motion processing engine that provides you scalability and fault tolerance. And so it's ideally suited for this high-speed ingestion, fault-tolerant ingestion. So we've looked at this as well. So apart from the engine, we have operators, ready-made operators, which came in very handy when building this application. For example, their input source was Kafka. So we had a ready-made Kafka operator that they could use out of the box, and the JSON parser that was ready-made as well. So this is just to show you what a DAG, how an application looks like. I mean, since you attended the earlier talks, you know a DAG, you know that it's composed of operators. You connect these operators. So here's a sample DAG. You could be reading events from Kafka. You're doing some filtering, and then you're doing some top N, and you may be basically to handle the data load, you may actually be having multiple partitions of these and processing these parallelly. So if you have two top 10s, you may want to combine and get the final top 10 before writing to the final output store, right? So this is just showing you a sample DAG application. And this is the operator library. So the specific library operators that they used were Kafka, and then the JSON parser, and they have a variant of, they used a variant of Cassandra as well. Later on, they did shift to a different data store. So you know about this application specification, so I'll briefly skip this for the interest of time. So why was Apex chosen? So one of the main reasons was it's fault tolerant, distributed, in-memory, rich set of operators, and basically it can ensure that you're processing data without any loss or duplicates, even in case of failures. The other operational capabilities where it's totally Hadoop native, so you don't need anything else. You can just run it on Hadoop Yarn. And you can easily deploy, monitor your applications using the DataTorrent console. And we integrate with the native security. So if you have Kerberos enabled on your cluster, SSL, it works with those settings. And you can also enable, on the console, you can enable different authentication mechanisms like LDAP, etc. So this is a skimmed version of the DAG. We cannot show some of the proprietary stuff. So these are two DAGs. The first one, essentially the stream source is actually reading from Kafka. This operator is actually, so this is getting JSON output, so each message is JSON. It's parsing the JSON, cleaning it up. If it's any bad records, it sends it to an error sink, which writes to a store. And then the data that's cleaned up, it's basically writing to actual data store on which further downstream machine processing is done. And then also they want to calculate, they want to bill their customer, right, on how much data is being processed. So they have a billing system, which basically this operator basically periodically publishes the billing stats to that. Right? The other things going on, but this DAG doesn't show that. And then this is an expanded version of the DAG, which basically applies alerting and rules on incoming data flow. Right? So for example, if a sensor reading has changed within the last second, you want to know it's an error condition, you want to send an alert. Right? Or if you didn't get a sensor value for the last 5 minutes, you want to know. So there are all these rules that need to be applied on data in motion. So you can't store it and then apply it later. You want to know it immediately. So this framework here, the rules framework, essentially with the operators handles that. And the way this was built is they could always add rules dynamically as the processing is going on, and the system would pick it up. Right? And imagine these rules could actually be thousands of rules, not just few 1 or 2, 3 static rules. So because different customer, there could be different rules for different customers. And it's a single ingestion application, right? Okay, so how was scaling achieved? So as you know, Apex supports different kinds of scaling mechanisms. So you have the default scaling, which is you can scale each stage independently. You can do parallel partitioning. You can also aggregate the results of all these partitions in a scalable way, in a sustainable way with cascade unification. So, and then of course you have dynamic partitioning, which basically lets you for things like Kafka, where it can elastically scale up and down. So this is a brief window of what their DAG looks like with scaling, right? So you can see, like there are 8 time series operators. So all these are like 8 partition Kafka, 8 time series. So it's all 8-way partition. I think this is the output writer. So so this is a cross section of this. So and here you're seeing this application in the monitoring console, which basically DataTorrent provides. So for each of these operators, they can actually see the stats, individual stats, overall stats. They can even see the worst path latency. For example, if this operator isn't performing up to par, so you can, and then let's say this is the path to it, you can actually see that whole path highlighted, and you can debug those problems. So some of the development aspects. So the CAFCO operator was used. So one of the properties of the CAFCO operator is this is a operator that has first-class support in Apex in our library. So we keep up with the version of Kafka. So if Kafka releases a new version of their API or they make some improvements, we try to mirror that with our Kafka operator. And so Kafka is like a in-motion, real-time in-motion message bus for basically consuming data or delivering data to different systems. So the way it does that is you have multiple partitions for a topic. So basically data is grouped by a topic, but each topic can have multiple partitions. These partitions could be on different machines. So you can actually, on the Hadoop side, parallelly ingest data from all these partitions, right? So you can have multiple processes in the Apex application, multiple partitions, each of them parallelly reading from the different partitions on Kafka. So you can, if you have n partitions, you could theoretically be bringing data at n times the rate of a single partition. So, but bringing data is one thing, right? Then you need to be able to process it also at the rate for the rest of the DAG. So that's where the partitioning of every stage comes in. So yeah, so this was used out of the box. And then some of the lessons learned with debugging was, so debugging, in general, debugging distributed systems is hard. So some of the features that Apex provides actually helps in this. The first thing is you can take your entire Apex application, and even before you deploy it in the cluster, you can run it locally within your IDE, so without any changes. So there's a test driver code that you can use and run it. So in this case, you can do breakpoints and other things in your IDE and debug your logic. Right? You can now, when let's say you do that and you launch the application, so now your application is distributed, running everywhere. You can actually look at in the console. You can actually look at logs for every container. So for every operator, you can look at the logs right in the console. So you don't have to SSH to that machine, or you may not even have access to those machines to do that. And if you have log aggregation enabled, you can use command line to get those logs. And then what also happens is we actually, in the console, you can also see, because you can see every container along with the app master, so you can actually see the entire topology of your application, and you can know what things are happening. And for example, if there is a container failure and a restart, you'll see that all right in the dashboard. So okay, for example, there's a failure, and the system took care of it by recovering. So you will see all those events. So you can know what's going on, and you can actually even publish those events into your own monitoring system. So if you're using something like New Relic or Nagios or anything like that, you can actually push those alerts there as well. So here's the application running. So what I showed you earlier was the physical view with all the partitions. This is called the logical view. So you can see these operators. You'll see only one instance of them. So essentially, this just shows the way you built the DAG and you connected them up. And then this gives you the combined metrics, right? So of all the partitions. So, but if you go to the physical view, you'll actually see the individual metrics of the individual partitions. So some of the challenges that we faced during this is GE basically wanted to be able to shut down an application and restart from a new version of DataTorrent, right? So essentially, let's say they have built an application, they basically want to be able to upgrade it and restart, right? So what today Apex provides is essentially a way to restart your application, but everything, your version and your code your jars have to be the same. So to do this, what we ended up doing is we saved state externally in a form that's independent of how the operator looks like. So for example, in the CAFCO Operator case, we took the offsets and we stored it in Zookeeper so that even if you totally upgrade your application and restart, we can pull those offsets. And then the external system that we were writing to for the usage metrics did not support any transaction semantics, so we had to implement the end-to-end exactly ones for that. So what it means is, so let's say we are writing to this external system in an operator, in the usage of how much a customer has been using the system, and let's say that node went down, right? So then the operator will restart from an earlier checkpoint, and it'll reprocess some data. Now we don't want to write those usage metrics again to the external system because we don't want to double bill the customer, right? And the external system couldn't tell us, hey, till what point we have already written. So we had to implement some code in that output operator, the operator that was writing to the metrics, to essentially not write duplicates. So we would actually store the information that we last wrote, so that we are not writing it again. And the other thing is, for the rules, we basically need to work with event time, the timestamp of the data. So essentially, let's say you get a particular metric, particular sensor value now, and then the next sensor value could arrive 1 minute from now, even though it was generated 1 second from the previous sensor value, right? Because of network delays and so on. So we need to be able to keep all the data, a large amount of data in memory, and be able to recall them, right? So we implemented scalable data structures that can hold large amounts of data with using HDFS as a cache. So key takeaways. So because of having the ability to store the offsets outside, we are able to guarantee upgradability of the application and restarts. The logging was useful. We went with dynamic partition for the Kafka because static means you basically have to pre-know how much resources you're going to use. And of course, the application development took a few months, and essentially at that time you're iterating and making changes and redeploying. So the console helps there. You can basically make your change, upload your application, run it, test it, and so on. And of course, we also built a tool that lets them benchmark their application, so they can run their application with different configurations. So for example, 8 partitions, 16 partitions, and then they can see the results, how much latency, how much throughput, and then they can, based on the need, they can pick the right configuration. Okay, so I also want to acknowledge my colleague from GE, Venkat, who is not able to be there today, who worked on this project, and he was a lead in GE. So with that, any questions? Okay.
I have a question.
Sure.
More of a Apache Apex question. You mentioned a couple of things for GE. One was that they wanted to do a bunch of stuff on the edge. I think that was like the first slide.
Yeah.
And you said all the machine learning that they were doing was on top or downstream of your technology. So how would you help GE or other companies like GE get that machine learning closer to the edge?
So it's a good question. So to be honest, machine learning is not necessarily a strong suit of Apex, right? We don't do machine learning per se, but if you have models that are already built, you could run those models in Apex, right? So the scoring part you can do on Apex. So that's what I would say. But we started to do some things around it. Like for example, we have loops in our DAG now, and we support a machine learning library as well. But yeah, I would say that there are more mature machine learning libraries that are out there.
Yeah. So can you repeat the question?
Okay.
We can ask a question.
Can you talk a little bit about how the time series data is integrated with non-time series data in GE's use case? I'm assuming there are data sources which didn't have time series context but was still relevant to the use case?
So in this use case, it was all time series data. So there was no like join of these streams like a time series and a non-time series. But we have other applications where we frequently have to join different streams of structured, unstructured data, or do lookups, enrichment lookups from traditional databases and so on. So we have models for that.
Okay. All right, thanks.
Yeah, thank you. Hello. Yeah. So I would like to understand the scope of DataTorrent in this whole system. Is it just ingestion? Because GE Predix has their own time series query service, right? So the whatever the DataTorrent team was responsible to ingest the time series data into their whatever the time series store they have.
So the time series service that you know of is internally using Apex and DataTorrent.
Oh, I see. Okay.
Yeah.
Right.
And yeah, so we are not providing a service externally. So they have built the solution with Apex
that service is powered by DataTorrent itself.
Exactly.
Okay.
It's powered by. Yeah.
Right. And the other question I had was you mentioned that they used to have the Cassandra as their store, right?
That was early phase. Now I don't know actually what they're using.
Okay.
So so it was during the initial POC phases.
Right. So I was just interested to know what are the factors they consider. In a typical time series store, right? So why Cassandra was not qualified for them? What are the challenges they faced?
Yeah, so one of the challenges I think is any store needs to be performant, right? Because your ingestion rate is going to be high. The store even should be distributed and needs to be able to handle the rate at which we can actually push the data out. Okay. So I would say, whatever store you're using that would be the primary thing for me to basically make sure that it's performant.